ஸ்பீக்கர் கட் பண்ணிருக்கோம்ல, அதான் நானும் போர்ட்ல அதுதான் எடுத்து விட்டேன். ஸ்பீக்கர் எடுத்து விட்டேன்.
Hello. So next, can we start, sir?
அதே சார் செஷன் ஸ்டார்ட் பண்ணலாம்.
Okay, sir. Okay. Good evening, distinguished guests, including respected professors, academicians, research scholars, and students. We extend a warm welcome to the fourth day of our 5-day online faculty development program, and today focused topic on understanding the Turing machine, a fundamental abstract computational model for simple processing and computation. It is our privilege to have you join us today. We are pleased to introduce our esteemed speaker, Dr. Deepa, Associate Professor. Ladies and gentlemen, it is our honor to welcome Dr.K.Deepa, Associate Professor at SRM Institute of Science and Technology, as our chief guest today. Dr. Deepa's expertise in IoT and deep learning models for agricultural enhancement is truly remarkable, and her contributions to the field are valuable. Within over 13 years of teaching experience, Dr. Deepa has inspired countless PTech students, and her online presence has reached even more learners. Her YouTube channel posts over 200 video lectures on theory of computation, artificial intelligence, and compiler design, with an impressive 21,000 subscribers and 7 million views. Dr. Deepa's commitment to making education accessible is evident in her additional YouTube channel, which offers over 150 videos on computer science, subjects in Tamil, Kataram, Malayalam, English, Hindi, Urdu, and sorry for interruption. With over 13 years of teaching experience, Dr. Deepa has inspired countless PTech students, and her online presence has reached even more learners. Her YouTube channel posts over 200 video lectures on theory of computation, artificial intelligence, and compiler design, with an impressive 21,000 subscribers and 7 million views. Dr. Deepa is a signing example of academic excellence and demonstrates her insights with audience over 100 Okay, sir. Dr. Deepa's commitment to making education accessible is evident in her additional YouTube channel, which offers over 150 videos on computer science subjects in Tamil, catering to rural students. Her publications on Udemy and Poem Plus portals, including 6 courses and a special course on genetic algorithm, demonstrate her education to sharing knowledge. With an impressive track record of 25 journal publications, 2 book chapters, 4 patents, and 1 patent grant, Dr. Deepa is a shining example of academic excellence. As a sought-after guest speaker, she has shared her insights with the audience over 30 times. Please join me in welcoming Dr. Deepa, a true pioneer in her field, and an inspiration to us all. We look forward to valuable insights and expertise, and we are honored to have her with us today. May I request all participants to kindly mute your microphones during the chief guest presentation to avoid any background noise and ensure a smooth session. Thank you for your cooperation. And now, without further ado, I am pleased to hand over the session to our distinguished speaker for today, Dr. Deepa. Please join me in welcoming her, ma'am. The floor is yours, ma'am. Please, ma'am.
Thank you so much, sir. Thanks a lot for that. A lot about it. Okay, thank you so much. I think we can start the presentation for today, right?
Yes, ma'am.
Okay. So today's presentation is regarding this Turing machine. My slides are visible, sir?
Visible, ma'am.
Okay. Okay. So first of all, a Turing machine is a mathematical model. We cannot even call it as a model. It is actually a machine, and this is an enhanced version of all those that you could have heard so far. Like in this 4 days presentation, we had a lot regarding this finite automata, push-down automata, and all the regular languages, context-free languages, and all. So this Turing machine is an enhanced version of all. So, like each and every model has its own restrictions, and there are certain things that can be done that cannot be done for the machines too. So, this Turing machine stands ahead of all the other mathematical model that we are going to learn in this theory of computation subject. So, I'll just go through what we have discussed in the previous mathematical models. So first mathematical model is a finite automata. So finite automata doesn't have any external memory unit. So what it can do, it can remember its current situations alone. So based on the current input, it makes some transition, and it doesn't have any external storage to store on what exactly happened for the previous movement and all. So whatever is possible right now, based on that, some action is performed, and that we call it as a finite automata. So it has a limited amount of memory. And the enhanced version of finite automata is push-down automata. So push-down automata has an access to a memory unit. So we have stack as a memory unit, but still we have some restrictions in stack. We cannot go ahead with the random access. See, whenever I want to add an element to stack, I can always access to the topmost element of stack. I can push an element or pop an element, or I can see what is the topmost element. So the only possible operation that we can perform with your stack is push, pop, and peek. And when I want to see what is the 10th element in my stack, that is not possible. The random access is not possible in case of your push-down automata. So these has its own way. Like when the storage is limited, when the access is limited, the language it accepts also is limited. So the Turing machine is the enhanced version of all the mathematical model that we have discussed so far in 4 days session. And we can call that like Turing machine is not exactly a model, it is a machine. For the finite automata or the push-down automata doesn't have any a machinery for it. Okay, there is no physical machine that operates on all this. So we have everything theoretically written. We have all the theories, theorems to be worked out on. But a Turing machine, we call that as a machine. The reason is it is an exact machine available that performs all the actions. So we can program a machine. So it is exactly like a computer. And this Turing machine has an infinite tape as a memory unit. So when there is a tape and the tape can move left or right, so when it is an infinite memory, it overcomes the drawback of finite automata, which has limited memory. And since a tape can be moved left or right, the random access is also possible. So that's why we call that as an enhanced model of this mathematical model that we have discussed so far. Okay. So I'll just show you one description, one video for Turing machine, so that first we'll know what a machine is, then we can come again on how to program for that machine. So this is a Turing machine, which has an infinite memory in both the sides, and there is a camera available, and there is a pen that is able to write something on the tape. So this tape consists of a binary, like it is like a bits. It can store one element at a time, and each time we can see what exactly is the content in the tape, and we can erase it, we can rewrite it. And this tape is like we have both the sides of tape available, we can move left or right. So there is a mechanism motor that can access this pen, erase it, and we can move left or right. So this is an exact machine that is available. And we are going to look into the programming constraint of this Turing machine. So this is an enhanced version of the mathematical model that we have seen so far. And this Turing machine was introduced by Alan Turing. So Alan Turing is the scientist who actually introduced this mathematical model, like we call that as a machine. And this is actually equivalent to that of the computers. Even now we use this Turing machine to prove something, whether it is solvable or not. Not all the problems that we have here are solvable, right? There are certain problems that still we need to find a solution for. So see, we use this Turing machine as an abstract machine to prove whether the problem can be solved or not. Even though it was introduced in 1936, we can equate that to a modern computers. But the programming constraint is there, like we have to program it in zeros and ones. It is able to access only zeros and ones, and but still we are using this Turing machine for checking whether the problem can be solvable or not. When you want to decide something as like when you want to decide some language as a decidable language or an undecidable language, we are using Turing machine for it. And this was introduced in 1936. And Alan Turing was he's an interesting person. Like he did a lot in this computing field. He's the one who introduced this Turing test too. How many of you know what a Turing test is? It's a bit out of syllabus, but still it is interesting. A Turing test?
Actually, we know that he was the one who was responsible for winning of the Second World War.
Yeah.
So actually, it was him who created a machine who was able to break the codes of Enigma, which was used by Germany.
Yeah, he's a cryptographer. Yeah, he actually worked for the company. Yeah, he did a lot. Like his age span is very small. Like he died in at his age of 36, but he did a lot of contributions in terms of this research in computer science.
Yes, true. And Alan Turing is the one. But Turing machine is on his name.
Yeah, Turing machine was his main, and his Turing test is also like we are still using that Turing test too. It is to check whether a computer can think like a human, like the thinking capacity of a human is related to a machine, right? So this intelligence
like GPT or what is talking about.
to check whether the machine can think like a human, and that test was introduced by him. So he did a lot of research in terms of computer science. Okay, now this is what I told you. A Turing machine, it is a finite state machine, but still it has a infinite tape as a memory unit, and the tape has each and every cell. The cell can store one element at a time. We have a read-write head. So the head consists of a camera. So that camera can look into what is the exact content that is available in the tape, and that it can erase the content, rewrite the content, and the tape can move left or right one cell at a time, like a king. One cell at a time, it has its possibility to move. And this can be equated to the computers nowadays. And how you're going to program this Turing machine is like this. Okay, so we have a finite control, and that control, this is an abstract vision of showing how a Turing machine exactly look like. The tape consists of all the elements, and we have one read-write head that can move left or right at a time, one cell at a time. And we have a place called control place where we can exactly store the program and And this program is nothing but the transition diagram we are going to give for recognition. So it has an initial state, final state, and current state. Okay, so any transition diagram that you give, it consists of one single initial state, multiple goal state is alive, and a special addition to the final state, we have a rejection state too. Okay, we all know that so far in all the mathematical model, we have one goal state or a final state to be reached, one or more goal state to be reached. In case of Turing machine, we have a special rejection state too. So when exactly we know that the input doesn't belong to the language, then we can trace it back to the rejection state. Okay, so this is how a machine works. So it is able to read one element at a time. Whenever we start the machine, the input will be written in the tape from left to right, and the read-write head will focus on the first element. So that is how the process actually starts. So the read-write head starts from the first alphabet of the input, and each time it is capable of reading the content on the tape. So I'll just give you one example. Then we can move on to the slides. Okay, I rather write it than with the PPTs. Yeah. So this is how a Turing machine operates on. So it has a infinite tape as a memory unit, and it is splitted in terms of cells. Okay, so the cells are capable of storing one alphabet at a time, and we have this read-write head that focuses on the first cell. So for our convenience, we freeze this leftmost column, like leftmost cell is freezed. Okay, and this is infinite. Okay, so this is the assumption we're going to have whenever we start a Turing machine. And I'll just give you one simple example, since it is already a fourth day in the FDP. All could have an idea of what kind of language a finite automata or a push-on automata could accept on. So I'll start from that place on. Say I'll take one regular language. So what is a regular language?
Language which is accepted by a finite automata.
Yeah. So regular language is something that is accepted by a finite automata. So finite automata is a mathematical model that doesn't have any memory unit. So if we can solve a problem without any memory unit, using a memory unit, whether you have a memory unit or not, still the problem is solvable, right? So I'll give you this example where I take one regular language and I'll show you how to construct a Turing machine for that regular language. I don't focus on the higher level problems. Rather than focusing on the higher level problems, we try to understand how to manipulate the small problems. Then we can go ahead with a higher version of it. Okay. So first of all, I'll take one language, and if the language is over the alphabet A comma B. So what does that mean? The input consists of A and B combinations, and I'm going to design a Turing machine that is going to accept something like this. If the input starts with A and ends with B. Okay, so this is my regular expression description. The input exactly starts with input A, and it is then followed by 0 or more A or B. So this A plus B denotes either A or B, and to the symbol of asterisk, like to the power of asterisk, means 0 or more combination. So that means the input starts with A, and that is then followed by either A or B or any combination of A and B, and that should exactly end with B. So that is my language understanding. I have the input should exactly start with A, exactly end with B. In between, I can have either A or B. We don't care about it. So what are the elements that this language will consist of? Exactly starts with A, end with B. So in between, when there is an asterisk symbol, it means that 0 or more combination. Okay, so we can have 0 combination of AB, or 1A in between, or 1B in between, or any number of A or B in between. Start with A, end with B exactly. So the language is infinite. It consists of a lot of strings that falls under the category input should start with A, end with B. Okay, so this is exactly a regular expression. Since we like this is a regular expression, we can solve this using the finite automata too. Now I'll show you how to construct a Turing machine for it. And whenever we design a Turing machine, or whenever we start Turing machine, the assumption is that the input is written in the tape from left to right. Okay, so we randomly write any one input out of this. Okay, so we have a lot of inputs here, lot of possible inputs here. So our assumption should starts with the input is written in the tape. So in the tape, I'll have input should exactly start with A and end with B. In between, I can have any combination. Okay, so for this, we are going to do the program, and it always starts with the starting state. So this is how a Turing machine starts. We have a tape, and the tape consists of all small cells. Whenever we start the process, whatever the input we want to check whether it belongs to the language or not, that is written in the tape from left to right, and the transition starts from the starting state. I'll parallelly construct a transition diagram too. So starting from this Q naught, I take Q naught as the starting state. Okay, now what we have to do is, as per our language, the starting input should be A. The Turing machine should exactly have A as my first element. So what I can do, I can create one more state On reading input as A, okay, the Turing machine has a read-write head that is capable of reading the element that is available on the tape. So it reads A, and our input should start with A. If it is exactly starting with A, then it is fine. What we have to do? We have to move right side, okay, until we find the B. Okay, so the last element, the first category is done. So first step is I have to start, the input has to start with A, it is starting with A, it is fine, well and good, right? So when the input starts with A, what is the next step? I have to check my last symbol. So last symbol will be there by transferring, like moving to the end. I have to move till the end, till I reach the end. So it is a right side move. So how I write a transition is, this A that is there in the tape will remain as it is. I make a right side move. This is how a Turing machine works. Each time it read the content that is there available in the tape, and if needed it will make some changes, and it make a right side move or left side move according to the problem that we are facing on. So here the input that is there in the tape is A. So I read it as A, it is fine. So I have to check the last symbol. So last symbol is available after making my move to the right side. So I make one step right. Okay, so is the first step clear? Since our language consists of two categories, input should start with A, end with B. For starting constraint, it is described here. And for ending condition, what we have to do is, how can we decide this is the last element? Okay, so there are certain empty spaces left in this tape. See these empty spaces that is there in the tape, right? That is represented using the blank representation. So B represents blank symbol. Okay, so blank means it is the input ends by this place and this is all empty. Okay, either we use B representation or this representation, anything is fine, but we have to initially give a representation to the Turing machine. Okay, so this is your empty representation. So to take my last symbol, okay, so I'll decide this is the last symbol if the next symbol is a blank symbol. So what I have to do, I have to travel till I find this blank symbol to make sure that I reach the end. Okay, so what I do is I put a loop here. Okay, the reason why I am adding a loop is I can have 0 or more A and B in between. Okay, so my input may consist of a A or my input may consist of a B. Whatever happens, I am just making the right side move. So first, after reading Q0 as A, it will make to the next cell to Q1. And this place may have A or B, we don't care about it. And this self loop, what it do, we'll just keep on moving until we reach this blank symbol. So each time it reads either A or B, and the tape will remain as it is, move right. Tape will remain as it is, move right. Until when it will move till it reaches the last symbol. So once it reaches the last symbol, what it means? The symbol before to it. Okay, the symbol left to it will be the last symbol. So I have to make one step, like Q1, I'm making a move till this place. So once I reach this last place, I make one step prior move. Okay, I make a left side move to Q2 state and check whether the last symbol is, I make a move to Q2 state and check the last symbol is B or not. Okay, and what we have to do, if the last symbol is B, we have to accept it. Okay, acceptance state is described using this double circle. So if the input starts with A, it is in a good condition. I will check the last element. So I make a move to Q1 state. In Q1 state, if the input is either A or B, I keep on traversing till I reach the last symbol. So to find whether it is a last symbol or not, I go till my blank symbol and come one step right. Okay, so that is what is done in this place. Okay, so all A and B, I keep traversing in Q1 state. And once I reach this Q2 state, once I get a blank symbol over here, I go one step left to Q2 state to check the last symbol. Now, if the last symbol is B, I'm going to a accepting state. When I'm going to a accepting state, this B will remain as it is. I can move right or left. That doesn't matter. I can just accept it. Okay. So this is about acceptance. When the input exactly follow this category, either A, B or whatever is the input that belongs to the given language, the input is accepted. But as I told you, this is not complete diagram for a Turing machine. The reason is we just have defined the acceptance state. We haven't decided on when the input has to be rejected on, right? So what exactly will be the rejection state? Instead of A, if my input starts with B, that has to be rejected, right? Whenever input starts with A, we have to accept it. So if it is not starting with A, then we have to reject it. And your input is made up of the combination of just A and B. Okay. So instead of in Q0, if the input is A, we have a transition defined. But in case if your input starts with B, I have to reject the input. Okay. So this is the rejection state. And I can just move left or right when I am making a rejection state. So what exactly a Turing machine will do is whenever it enters into a rejection state, the thing will be stopped. The machine will not move. Similarly, whenever it enters into an accepting state, the machine will not move. It will stop. Okay, I'll just show you an example, some of the examples too. Okay, similarly, the input should exactly start with A and the input should exactly end with B2. So in Q2, instead of B, if you have a, then also it has to be rejected. If the last element is A instead of a B, we have to reject the input. Okay, now it is complete. Okay, now we can call that the transition diagram is completely defined since the input starts with A. We have a transition and that will check the end of your transition to end of the end symbol also. If the input ends with B, we are accepting it. But in case instead of A, if your input starts with B, we have to reject it. And similarly, in Q2 state, if the last element is A instead of B, we have to reject it. Okay. Now this is a complete complete model for a Turing machine. A transition diagram that has a starting state Q0. Only one initial state is allowed for any Turing machine. So now the initial state here is Q0. And we can have a multiple final state. So here only one final state, acceptance state is there, that is Q accept. And we have one rejection state defined, that is also clearly done. Okay. So this is how we design a Turing machine. So each step of a Turing machine will have all this process. So that is what is defined here. So what we do, based on the current state and current tape symbol, we can like the read-write head can look into the tape what exactly is the symbol is, and we can rewrite the symbol. Okay, write a new symbol on the current tape, and we can make a left side move or right side move, and we change the state. And this process is iterated until we enter into accepting state or a rejection state. Okay, it is an automated process. Whenever we start the machine, it actually starts working on it. And until it will run until it reaches either an acceptance state or a rejection state. And in case if there is nothing defined, it will stop. Okay, so this is how a Turing machine will work on. And this overall the tuple notation. When you want to formally define a Turing machine, this is the symbols that we use to define a Turing machine. Like we have the same kind of symbols in case of your finite automata or a push-down automata. So first you have Q. Q is set of all possible states. In case of the example that we have discussed, we have Q0, Q1, Q2, Q accept, Q reject. So we have 5 states there. So it is a finite set of states. There are countable number of set of states that are available. And we have sigma. Sigma is for the finite input. What all the input that are allowed to have here. So in the example that we have discussed, the input is made up of the combination of either A or B, right? So that is your input symbol, and this tau is the element that we can written, that can be written on the tape. Okay, there are certain restrictions that I can add these kind of elements alone in the tape. In the example we have discussed, we have A, B, and we have the blank symbol that is written on the tape. So all these things comes under tau. And for the blank representation, we use a symbol, right? So that will be B. And F is your final state, and that final state consists of Q accepting and Q final state. Q accepting and Q reject state. Okay, so F consists of finite set of states that includes Q accept and Q reject state. And you have only one initial state. See, for initial state we use Q naught, only one initial state. But for final state we have set of final states. Okay, you can have multiple acceptance states and multiple rejection states too. So that is accepted. So that is why we have this capital letter F. And the very important thing that you want to listen here is the transition function. So the transition function here is given as like how does a move actually happens in case of Turing machine from a state on something that is written on the tape. Each time the Turing machine will look what is there on the tape and it make a move. So that's why we have this Q and tau. Okay, so based on the current state, based on the current element that is there on the tape, and what we are going to do, we make a transition to the next state on writing something more or different into the tape, and we can move left or right, and sometimes we use this H symbol, like some of the model actually use this H for halt condition. Whenever we enter into acceptance or rejection state, we use this halt symbol here. Okay, so this is how a tuple notation will look like for a Turing machine. I'll write the Turing machine symbol here. So here, this is my transition diagram. And in the transition diagram, I'll write all the tuple notation. So Q is my set of all states. So Q includes Q0, Q1, Q2, Q accept and Q reject state. Okay, and your input consists of, see, input is made up of the combination of A and B. Input consists of A and B. And the element that can be written in the tape is state consists of A, B, and a blank representation. Right? And remaining things the same. We have Q naught as the starting state, capital B for the blank representation, and F consists of Q accept and Q reject state. Two final states, Q accept, Q reject state, we have it. Okay. Now what is left out? The transition function, right? The way we represent a transition function. I'll write very few transition functions alone. So starting from Q naught, when the tape consists of A, what we do? We make a transition from Q0 to Q1 state. So we can write it as Q1, and we didn't change anything on the tape. Okay, so this is a place we are not going to make any move over here. So A will remain as it is in the tape, and what we do? We make a right side move. That is this description. Q0 on learning, the tape consists of A. So it is in a Pakka way. The input is exactly starting with A. So I just move to Q1 state. So this is how we write a transition function. And similarly, you can write a transition function as Q0 when the input is B. The input should actually start with A, but here it is starting with B. So I have to reject it. So it is making a move to, so this is this path. Okay, so we are making a move to Q reject state. The B remain as it is. Now I can move left, right, or halt is also fine. Okay, so this halt symbol is defined by some of the machine actually allows this halt and some of the machine will not allow this halt. Anyway, you can write it. Okay, so these are all the machines or these are all the tuples that we have for a Turing machine. Okay, and we can also use a tape representation. So this is one way of representing a Turing machine using a transition diagram. Another way is we can use a tape a transition table representation too. Okay, and the tape representation is like why we are allowed to use this transition table representation is since your initial input is depending on the state and the tape symbol. Got it? We cannot use a transition table representation for push-down automata. You know why? We use the transition table representation for finite automata, that is allowed. But push-down automata will never have a transition table representation. Anyone guess why? Since the transition of a push-down automata happens like this, from a state on an input on something on the tape, we make a transition. Okay, so it consists of three elements, and these three elements cannot be represented using a two-dimensional array. Okay, so to a two-dimensional table. So that's why push-down automata will never use a transition table representation, but for finite automata and Turing machine, we have a transition table representation. So one side we have all set of states, another side we have a tape symbol. Okay, so why we have a tape symbol? Since the transition is based on the tape symbol. And what all the tape symbol that are allowed for a Turing machine? For this example, tape symbol consists of A, B, and a blank representation. And your states include Q0, Q1, Q2, Q accept, and Q reject. Okay, and which is your starting symbol? Q0 is the starting state. So we use this representation whenever you are using a starting state. And the final state is represented using an asterisk symbol on the top of it. Okay, so the tape can be filled like this. Q0 when the input is A, this is your final outcome, right? So I can write everything here. It moves to Q1 state, A, and R. So similarly, you can fill Q0 on A. On blank, we don't have a transition, so we can just include a hyphen for it. Okay, so this is how a Turing machine actually works. So what we have discussed so far, what is a Turing machine, how does it works, and what are the tuple representation for the Turing machine. And I have shown you an example for the transition table and transition diagram representation. And there is one more thing that we want to look into it, and that is like, when can you say that the input is accepted or rejected? So we have to take an input and check whether it is accepted or not, right? So you should need a continuous flow in that case. So I'll just give you one example. Okay, to check whether the input is accepted or not. Usually we do it in case of your finite automata and all, right? Like I take one input and the input consists of, I'll take a simple example. Okay, A, B, B. Okay, the input has to be accepted. I'll take an example where the input is accepted by it. So usually we use this W to represent whether for the input. And what we said here, in case of a Turing machine, we have this representation. Okay, whatever might be the input, the input is written in the tape from left to right. Okay, and the transition actually starts like this. Okay, in case of a Turing machine, just give me a second. Sorry for the interruption. Okay. Now this is how a Turing machine is designed. Like whenever you want to check whether the input is accepted or not, the input is written in the tape from left to right. And we have the starting state focusing on the first element on the tape. And what about the remaining conditions that we have discussed? Like the tape consists of all blank symbols for the empty cell representation. Okay. So what we have to do, we'll go ahead as per the transition diagram. So in Q0, if the input is A, what we have to do, we make a right side move to Q1 state. So the next step here can be given like this. A will remain as it is. So there is no change in the tape after the first transition. And we just move one step right side to the next element. Okay, so from Q0 on reading the input as A, we make a move to Q1 state. and Q1, if the input is A or B, we keep on moving right. So the next step here is given like so we have the same tape diagram. Have this blank representation. Q1, when the input is B, it make a right side move to the same state. Since it is a self loop, what is the meaning of self loop? It will stay in the same state and make a move to next step. Okay, and here and Q1, when the input is like what exactly the purpose of Q1? It has to move till it find a blank representation. So once in Q1, if it find a blank representation, what it do? Q1, when the input is blank, it make a move to Q2 state. So this ABB will remain as it is. See, we haven't changed any content in the tape. Content remain as it is. We make one step ahead to left and we make a move to Q2 state. And what is the purpose of Q2 state that we have decided? It checks the last element. In Q2, the input is B. We are making a move to Q accept state. So the next step in the transition is like this. This ABB will remain as it is. And we make a right side move to Q accept state. And whenever a Turing machine enter into a accepting state or a rejection state, the input will be accept. The Turing machine will halt. Okay, so it is not like what you have discussed in terms of your push-down automata or a finite automata. So in case when I want to accept a language in case of finite automata or a push-down automata, I have to completely transfer till till the end of the input. But for Turing machine, whenever the transition enter into accepting state or whenever the transition enter into a rejection state, the input will be rejected or accepted. Okay. So here we have, this is called tape representation. Okay. We are visualizing the tape each and every step. But formally, when you want to represent the instantaneous description of a Turing machine, we have to write it like this. The content in the tape will remain as it is. We have to add this state in front of, like to the right of the tape place where this read-write head is focusing on. So in this place, read-write head focus on the first element. So I'm writing Q0 followed by the element that is there in tape. Okay, so this is called instantaneous description. At the instant, how can you visualize the things that are happening in a Turing machine? So when I start the process, your input is written in the tape from left to right, and the read-write head is focusing on the first element. Okay, so Q0 comes at the first. Okay, I write an instantaneous description for it. So now Q1 is the state, and that is there focusing on B. So the instantaneous description for this is A, Q1, BB, and the blank representation. So wherever your read-write head focus on, you have to write the state in front of it. Okay, and for this AB, and this is the place where you have a read-write head. So write Q1 in front of it, followed by BB. Okay, and for this it is ABB Q1 blank representation, and for this it is AB Q2 B blank representation, and for the last it is AB B Q accept blank representations. Okay, you can have any number of blank symbol, that we don't care about it. Okay, so this is how we write an instantaneous description, and we use this symbol to represent that from the state after making a transition, we are moving to this state, right? So from instantaneous description means like after this step, Q0 when the input is A, it make a right side move to Q1 state, and this is the instantaneous description of that. Okay, so this is called move of a Turing machine. From this state, I'm moving to this state, and from this, I'm moving to this, and from this, I'm moving to it, and finally, I'm moving to this place. Okay, so this symbol intimate that it is a move of a Turing machine. Okay, and when I add this asterisk on top of it, on 0 or more step, I am able to move from this state to other state. For example, starting from the initial state, I'll use another color. Starting from Q0, A, B, B, all blank representation, I'm able to reach the final state on making a move, right? So this is the last step. I can write it as A, B, B, Q except blank, blank, blank representation. So on multiple moves, I am able to start from this place. I am able to reach this place. Okay. So this is a move of a Turing machine. Got it? So I'll just go through the slide once. Any doubt in this so far?
No, ma'am. Everything is clear. Proceed with presentation.
Thank you. So there are two different descriptions that we have discussed on. One is transition diagram. Another one is the transition table representation. Okay, and what is a move of a Turing machine, language acceptance, and instantaneous description we have discussed on. So instantaneous description is something where we are going to write the state in between, in front of the start of it, in front of the place where the read-write head actually focuses on. And language acceptance is whenever a transition enters into the accepting state, we are going to accept it. Okay, see here you have this asterisk symbol, right? On multiple moves, we are able to start from somewhere and we are able to reach to the final accepting state, then the input is accepted. So whenever a Turing machine stops, we are going to accept it. Okay, and we have this important definition called Turing decidability. Okay, so we call some language as a decidable language. Whenever a Turing machine exactly says that this input belongs to the language or this input doesn't belongs to the language. Those that we have discussed in the previous example and all, we can directly say that the input is accepted or not. Okay, so we can design a Turing machine for it. And these are all the possible states. For the example that we have discussed in the previous, it says that when the input exactly belongs to the language, we are going to accept it. When the input doesn't belongs to the language, we are going to reject it. Okay. So when this is possible, this machine will always halt, right? So we call these kind of language as a decidable language. But there are certain conditions that are happening in case of your Turing machine too. Sometimes we will reject, sometimes we will accept, and sometimes we will enter into a looping state too. Okay, so we cannot decide that initially too. Okay, there are possibility where a machine will enter into a looping state too. Okay, so when a machine enter into a looping state, the machine is not going to stop. So we call these kind of places as undecidability. Okay, when the input belongs to the language, we're going to accept it. When the input doesn't belongs to the language, if it always reject and halt, it is decidable. But sometimes if it enter into a loop, then we call those kind of languages as an undecidable language. Okay, so we are using Turing machine and the theorems even now to prove that something happens here and still there are undecidable problems exist. Okay, and there is one more thing that we have to know, right? So for all your finite automata or a Push-on automata or a Turing machine, whatever you have discussed so far, will check you that whether the input is accepted or not. Okay, so we call these kind of languages as a language acceptor or a recognizer. Okay, we are going to verify whether the input belongs to the language or not. But Turing machine is an enhanced version of all these things. Okay, so it can be used as a computable devices too. So computable devices in the sense like we can perform addition, subtraction, multiplication, everything in terms of using a tape. That is also possible, but the coding might be a bit hectic here. Okay, so what we have to do it in zeros and ones. Okay, so not even zeros and ones, we have to code it in a unary constraint. Okay, that is also allowed. Like we can use Turing machine as a computable device. And there are some examples for addition, subtraction, multiplications that are allowed that can be performed in a Turing machine. This is your language acceptance. This is one example like what we have discussed. This is your palindrome example, but we don't have time for explaining these big questions here. Okay, and computable devices also, it is allowed. Like this is how your input will look like. It is all unary representation. Okay, so when I want to add two numbers, I have to represent two ones for all in ones. When I want to add 3 plus 2, I use 3 ones to represent 3 and 2 ones to represent 2. It is completely unary, but we can perform all the arithmetic calculations in unary operations. Okay. And there are certain variants that are allowed in case of Turing machines, like variants in the sense like what we have discussed is a single tape Turing machine. There is one tape, one treated tape, we can make a transition into it. And there are multiple ways in which a Turing machine can express on. One is two-way infinity. So what in the previous example, we saw that one side of the tape is freezed. When we are writing content in the tape, we write from left to right, not in the entire tape. But the enhanced version will be there are two-way infinite tape available, and we just have one track. We can have multiple tracks, multiple tapes, and even non-deterministic Turing machine too. So what is non-determinism? From one possible constraint, one possible scenario, I can have a multiple outcomes. Okay, from a state on something on the tape, on some one specific symbol on the tape, I can have a multiple transitions too. So that is your non-deterministic Turing machine. This is two-way infinite tape, but everything is equivalent. What does equivalence means? We don't call that as an equal. It is equivalent. So equivalent is something when everything except same kind of language, whether you have a two-way infinite tape or a non-deterministic Turing machine or a multi-tape Turing machine, everything except same kind of language. If I am able to solve the problem using a single tape Turing machine, I can solve it using non-deterministic Turing machine. I can solve that using multi-tape Turing machine too. And similarly, if I am able to solve one problem using this multi-tape, multi-track Turing machines, then I am allowed to solve the same in a single tape Turing machines too. So we have these conversions too. There are certain conversions that happens between these tapes. Okay. So this is non-determinism. On one instantaneous description, I can have a multiple possibility. Okay, from a place, I can have multiple possibilities. This is also allowed. This is multi-tape Turing machine. I can have a multiple tapes here. And for equivalence, I'll just skip this. So this is how equivalence happen. All the multiple tapes can be simulated in a single tape too. And similarly, multi-track is also available. Okay. And the last topic about like when we start discussing about the problems, when we start solving the problem, we'll have a lot to learn in Turing machine. Okay, so it is not one single session enough to cover the complete things into it, but I'll just give you a description of all. Okay, so there is something called an universal Turing machine. Universal Turing machine is nothing but we can simulate another Turing machine into we can give a description of other Turing machine into a Turing machine. Okay, it is like we create a program to create another program. Like we have an operating system, what operating systems or compilers and all, right? Compiler itself is a program, but that is used to compile other programs. Okay, so that is how a universal Turing machine is. We can just compile or we can just justify all the codes of a Turing machine and we can represent it as a binary codes. Okay, so this is how a universal Turing machine will look like. This is how we prove all the theorems. Okay, universal Turing machine is again it can be simulated by other Turing machines too. So this consists of when I want to simulate a Turing machine, I should know what is the machine and what is the input for. Okay, so I take M. M is the description of the machine and W is your input string. I'm going to combine these two. Okay, and we are going to convert that into a description. And as we discussed, your Turing machine will be operated on a unary constraint. Everything when you want to code in a Turing machine, you have to code it according to a unary constraint. For example, if I have alphabets, the input symbols, I can code the first element as 1A, A as one single one, B as 2 ones, C as 3 ones. Okay, so this is how we represent a coding. This is called encoding process. Like a Turing machine will have 7 tuples, and all the 7 tuples can be converted into an encoded structure. Okay, for alphabets we use this, and similarly for state also we can use one represent state 1, and 2 ones represent state 2, 3 ones represent state 3, and similarly left side move state 1, right side move can be encoded with two ones, and the transition symbol also can be given like this. So Q1 we use 1 as a Q1 representation, and for A also the symbol is 1, and to separate these two we use 0 as a delimiter or a separator. Okay, so Q1 when the input is A, it is making a transition to Q2 that can be encoded as 1 0 1, and after transition it moves to Q2, and for Q2 we use 2 ones as a representation, right? We use this 2 1. And similarly, B is represented with the 2 ones, and left side move is represented using 1 1. So we have to completely encode all the transition function in terms of unary constraint. You have to convert that into a unary form. So this is how the final conversion will look like. And for one transition to another transition, I have to split it, right? I use 2 zeros to separate it. Okay, so this is how universally we convert one form to another form. Okay, so this is your universal Turing machine. So once it is programmed, then this can be given to another Turing machine to work as an input. Okay, so this will help in case of proving some theorems. When I want to prove something as a decidable problem or a halting problem, we require a universal Turing machine to prove that. Okay, so there is a lot. This is one simple example that we can give. Okay, so with this I can just put a hold. I haven't given the complete description, but I just gave you what a Turing machine is, how a Turing machine works, and how to represent it, and how it processes input, acceptance, language acceptance, followed by a universal Turing machine. So if there is any doubt, please feel free to start.
Participants, any doubts? Okay, thank you, ma'am.
Yeah,
Dear
this
guests
is
and
my
participants,
this is my channel. Like if you want to learn a lot about Turing machine, or regarding the other topics of Turing machine, I have my channel online. You can search for Deepa content. So I have around 200 300 videos related to all the subjects of artificial intelligence, theory of computation, neural networks, and all. And there is a channel in Tamil that also covers up these topics in regional language. And there is one Udemy course I exactly posted for learning this theory of computation in Tamil. If you want, please ping me. And there are other courses too available. And I have posted one of my course in Swayam Plus portal too. So if you need any help, or if you want to contact me, please mail me. I'll share you all the links where you can take up the course for free. Okay, there are constraints that I want to satisfy. I cannot post a free course. The reason is like there are some restrictions. Okay, since this is a vast topic, the number of hours of recording is more, and that doesn't satisfy my free course constraint. So always text me or mail me. I'll share you the links where you can take up the course for free. Okay, if there is any help, please contact me. And thank you so much for your patient listening today.
thank you, ma'am. Dear guests and participants, we are deeply grateful to Associate Professor Dr.K.Deepa, our esteemed resource person, for sharing invaluable insights of the Turing machine during our session today. Your expertise and engaging presentation have enriched our understanding and inspired to us explore new avenues. Thank you, ma'am. To our participants, we thank you for your active engagement, thought-provoking questions, and enthusiastic participation. Participants, kindly fill out the feedback in addition to your passport size photo for certificate purpose. Thank you, participants. All the participants are required to attend tomorrow FTP session. Additionally, your feedback tomorrow is mandatory to receive your certificate. Thank you for your cooperation. Thank you all.
Thank you, Deva ma'am, for sharing your insights. It was really helpful.
Thank you so much, ma'am. Thank you so much, sir.